Number 1. Let f be a parabola whose vertex is at 2, -1. If g of x equals f of x minus 2 plus 3, state the vertex of g. Explain your answer using transformations. So I know that this parabola, and assume it's concave up, has a vertex at 2, -1. This is the graph of f. So this red function is f. This function g can be obtained using this transformation here. That transforms it up 3 units. And then remember, this is not really a -2, it's really a +2. So that goes right 2 units. So I need to take that vertex and translate it using these shifts. Right 2, up 3. So my new point has an x value. I went right 2 of 4, and up 3, 2. So the new vertex is the point 4, 2. Explain your answer using transformations. Well, we translated f, right 2 and up 3, to obtain the new vertex. The whole parabola shifted up to right 3, but I know that's the new coordinate of the vertex. It's not just the quadratic function that we can transform using these transformations. If the graph of y equals f of x is shown below, sketch a graph of g equals f of x plus 4 minus 5. Explain how you obtained your answer. So, looking at this here, g is a transformation of f. I transform it down 5 units, I shift it down 5, and that's not a plus 4, that's really a minus 4, so left 4 units. So I need to transform this graph down 5 and left 4. Down 5, 1, 2, 3, 4, 5, left 4. 1, 2, 3, 4. Down 5, 1, 2, 3, 4, 5, 1, 2, 3, 4. Down 5, 1, 2, 3, 4, 5, 1, 2, 3, 4. And finally, down 5, 1, 2, 3, 4, 5, 1, 2, 3, 4. All we're doing here is we're just performing a translation like you did in Common Core geometry, a whole bunch. So, this new function here should be congruent to that original function. If that's f, this is the function g, because a translation is a rigid motion. So these two functions are congruent because I just performed a translation. I slid it along the plane. So explain how you obtained your answer. We translated f left 4 units and down 5 units to obtain the graph of g. 3. Write the quadratic f of x equals x squared plus 10x minus 2 in vertex form. So to change from standard form to vertex form, we need to complete the square. And I need to state the vertex. So, if f of x equals x squared plus 10x minus 2, I really care about this portion here. And using an area model, that's x squared. I'm going to split that in half into 5x and 5x. So that's x times x plus 5 plus 5. Well, 5 times 5 is 25. So 25 is the special number that I need to add to complete the square. So I get x squared plus 10x plus 25. Well, I can't just add 25, so I'm going to have to also subtract 25. So I make sure that I'm not actually changing the value of the expression. Well, this expression here is a perfect square trinomial. I know that x squared plus 10x plus 25 is x plus 5 times x plus 5, so that's x plus 5 squared, minus 27. So now f is in vertex form. And I know it has a vertex of, well, that's shift. Let's talk about the shifts here. This is take x squared, shift it down 27, down 27. So shift it down 27. And remember, this is opposite, so left 5. So it's 0, 0, going down 27 and left 5 gives me a vertex of -5, 27. That's the vertex of this parabola. So to go from standard form to vertex form, you have to complete the square. If you're fine with half a b, square it, that works too, or use the little area model to help you out. 4. Let g of x equal this function. Graph the function y equals g of x on the set of axes. So, you could use a calculator, but this is in vertex form, so we can just use transformations to get us there. I'm going to start with graphing y equals x squared, just as a reference. There's my parent function there. And I'm going to shift it left 2. So left 2, up 1. Left 2, up 1. Left 2, up 1. So my new vertex went from 0, 0 to that new point. I know it's concave down because A is negative, and it's going to be wider. It's going to be wider and concave down. So again, this is a complete rough sketch, but it's concave down because A is negative, and it is wider because 1/4 is less than 1 and greater. It's between 0 and 1. It's a fraction that's between 0 and 1. So that's a sketch of this function just by using my calculator. This is g of x. That's x squared. The green one, the dashed one, is the parent function there. What is the vertex of g? Well, the vertex is left 2, up 1. Negative 2, 1 is the vertex. Is g concave down or concave up or concave down? It's concave down because a is negative. Because a is negative, it's going to open downwards. What's the range of g? Range is your y values. Range is your y values. How high and low do my y values go? Well, I know the highest point my y values go is because this vertex here is a maximum, is 1. So my y values are less than or equal to positive 1. I get every y value less than negative 1. That's as high as they go, and I can get any y value less than that. So less than or equal to negative 1. And finally, number 5. Remember that a function is considered even if it has symmetry across the y-axis. So a function is even if I can reflect it across the y-axis and get the same function back. Sketch a graph of f of x equals x squared. You should be pretty comfortable sketching a graph of x squared. And justify that it's even. Well, x squared is even because it's symmetrical across the y-axis. It has symmetry across the y-axis. If I find f of negative x, you just get back f of x. Because what's negative x squared? Well, that's just x squared. So if you plug in a negative x to the function, you get back the original function. It's symmetric across the y-axis. Let g of x equal f of x plus 2. Is g even? Well, what shift happens here? That shift up 2. So if I take this parabola, if I take my parent function and shift it up 2, is it still symmetrical across the y-axis? Yes, it is. It is. Because all I did was I shifted it up 2, I can still fold it across the y-axis and get the same thing on both sides. It is symmetrical, it has symmetry. There is symmetry across the y-axis. I can reflect it across the y-axis and get the same function. And finally, h of x. Let h of x equal f of x plus 3. So I'm shifting left 3. I'm shifting left 3 units. So let's actually do that. Let's take our parent function, x squared, and shift it left 3 units. Is that red function there? Is it an even function? Is this red function symmetrical across the y-axis? And the answer is no, because it doesn't have symmetry across the y-axis. No, you cannot reflect it across the y-axis and get the same image. You cannot reflect across the y-axis and get the same image. It didn't get carried onto itself. It would be this new function. It would be this new function that looks something like, if I reflect this across the y-axis, it's going to look something like that. And that is not what I want. That is bad. So I'm going to undo that. This function h is not even. Is it an even function? No. Where g, the answer was yes, because I just shifted it up 2. Hopefully this lesson was a review from Algebra 1 about shifting our parent functions around, especially quadratics, and getting into vertex form and seeing how much more powerful that is than factored form of a parabola.